Hello, my name is Vivian Liu, and I am a first-year PhD student at Columbia University. I'm presenting a demo titled Neurosymbolic Generation of 3D Animal Shapes Through Semantic Controls. This work is done in collaboration with Professor Lydia Chilton, also at Columbia. So our research problem focuses on animal shapes. Designing 3D animal shapes is a hard but very common task. We come across animal shapes very often, whether it's through animated movies, games, AR content, educational content, stuffed animals, or the like. They are one of the most common classes of 3D assets created. However, they are hard to create because they require significant 3D modeling expertise, as well as a non-trivial amount of geometric intuition. Now, state-of-the-art work in artificial intelligence has shown us that generative AI can generate 3D shapes. We could sample shapes from latent spaces, which are the internal data distributions that AI learn. However, when we expose user controls over those latent spaces, we find that it is hard to interact with them, and that is because the axes of these latent spaces have no intuitive meaning. So, for example, on the sliders we see here, which map to axes of the latent spaces, there are no labels, and that is because every single axis is too hyperdimensional and entangled for us to attach any semantic meaning to them. However, recent work has shown that 3D generative AI can learn semantic parameters alongside shape. Work out of Thomas Funkhauser's lab at Princeton last year posed the concept of a semantic space. The idea is the following. The idea is that perhaps there are only a few things that really matter when we're defining a 3D shape, at least at first. So let's take the chair on the left here as an example. If I'm referring to this chair, I might talk about it in terms of some low-level salient features, such as its height, or the length of its legs, the depth of its seat, the height of its backing, etc. Now, what if we could guarantee that the model learns these signals by feeding it an exhaustive amount of synthetic data, so that we could guarantee that the model sees all the variants we think it possibly needs to see? So that's like showing a model all the different possible chairs by creating a template chair with thousands and thousands of variations. I call this template chair a meta shape in this demo, a generic low-fidelity shape that can abstractly characterize a class of 3D objects. We created animal meta shapes as synthetic data to learn a semantically meaningful latent space. And here are some examples of the animals created for this purpose. Our meta shapes were symbolically parameterized by animal limbs, as well as simple operations like translation, rotation, and scale. They were generated from sets of metaballs, which are 3D primitives that additively and subtractively react to one another to coagulate into organic-looking shapes. We trained a model jointly on this real and synthetic data, supervising on semantic labels as our ground truth. Now, the reason that this paper is titled Neurosymbolic Generation is because the model is learning neurally in a data-driven fashion, but also symbolically. It is learning semantic meaning over the latent space based on the symbolic constraints of the animal metashapes. So in this diagram here, I'm visualizing the multiple input, multiple output autoencoder model that we implemented. This encoder and decoder shares structural similarity with both Funkhauser's work as well as with the seminal point net architecture. So our preliminary results showed us that our system and approach could generate a diverse range of animal shapes beyond what was simply captured in our synthetic dataset. Additionally, we saw that the model could learn semantically meaningful signals. For example, we see here that by adjusting the torso length slider, the torso length is truly changing in response. And likewise, by adjusting the neck length, the neck of the animal meta shape changes accordingly as well. However, it seemed like our meta shape was too low fidelity because the model would sometimes get confused between the neck and the tail. On the screen here, we're changing the tail rotation, but the neck rotates instead. Therefore, we created higher fidelity meta shapes, parameterized by 23 axes as opposed to 6. We then created a UI featuring this larger set of semantic controls and conducted pilot user studies to understand their user experience. Now I will take you through a walkthrough of our user interface. So here we have a big picture of what the user might be seeing as they are defining their shape. Their main output is in the center. It reacts to the semantic sliders, which are depicted on the left. These labels map to the symbolic parameters that originally defined the synthetic data. To add interactivity and depth to our generative AI's user experience, we also added other features to our UI. Users could utilize a grid view seen on the top right quadrant, which demonstrated different shape edits that users could launch to from their current shape. And on the bottom right quadrant, we have a visual bibliography, which shows 3 training data points in the form of higher fidelity point clouds. These 3 point clouds are the most similar to the current output along one semantic dimension of the space. The intention of this functionality was to make the internal data distribution of the AI transparent to users and to acknowledge the contribution of original artists in the AI output. Users can save their shapes by clicking on the save icon below. This implements the concept of system memory, which is a recommended feature in computational creativity systems. So the task for the users was the following. Imagine that you want to create a game like Pokemon Go or Neopets. You want a diverse set of creature-like characters that are inspired by animal shapes. So from there, participants used our user interface to create 20 animal shapes in 2 rounds. In the first round, the grid option was more modest, so users were encouraged to focus on the semantic sliders. Here we see a participant working on creating their shapes with a goal in mind to create sea creatures. Here we see another participant working on creating 10 shapes with a more reactive and random grid. The grid offered an exit route when the semantic sliders stopped satisfying the user. And we observed that users tended to use the interface with the following pattern. The semantic sliders helped define local changes on their shape, while the grid view offered them larger step changes away to new shapes. So here we can see a zoomed-in version of the semantic sliders. Again, we can see that some labels are learned better than others. For example, tail length and tail radius seem to have corresponding effects. However, tail rotation again leads to rotation of the neck and some entangled effects with the head. So users did find it hard to map semantic labels to AI behavior because the mapping was not as tight with 23 parameters as it was with 6. So as this participant says, the sliders definitely helped me control the shape, but it was often hard to map their description to exactly what it did. However, using the sliders did give participants a sense of ownership and control. Another participant said, I kind of feel like I have to change the sliders a bit to feel like it's mine. So a recurring and very frequent theme was that users would interpret their animal shapes with personification and creative liberty. So participants would qualify their shapes with attributes. For example, they would say, oh, this looks like an owl with a fire butt, or a plump canary, or a very hilarious animal with a flat face, like it's the pug of lizards or something. So they would hybridize animals as well. We also noted that they would personify them. So this participant said, this is kind of like a funny animation, like it gets shy, and then they would adjust their tail radius, and then it gets tall and proud. They also would veer away from completely realistic shapes and look at more amorphous routes and non-realistic shapes. So this participant said, this kind of looks like a amorphous blob. I kind of like that. This looks like a pile of leaves. And then they saved that shape. They also went on to make one that looks kind of like a ramp. And then they thought, maybe these are like Play-Doh creatures that are living in the universe as well. This one could be like Muck, Pokemon, or Ditto. So often, users would also conceptualize the design space. So here a participant says, this is like very cute, we're in Loch Ness Monster territory. So they were understanding a space, a sub-portion of the design space. However, they were also finding bad spots or extrema that they were landing in. For example, this participant said, I just feel like I'm stuck with the salamander poodle. I just want to take this somewhere completely different. So a lot of the participants ended up using the sliders more like switches. They would either minimize them or maximize them very fast. They would do this to understand the effect of the AI slider, but at the same time, this was also a user interface caveat. And another user interface caveat was that there was no means for direct manipulation, and some users expressed the desire to just, for example, if they wanted to make a hip, add clay into the shape output. So here are some galleries capturing our participants' co-creative experience with our 3D generative AI. Some had goals in mind and some did not. At any rate, I hope you enjoyed this demo, and thank you very much for listening.